Homework 35, page 340, chapter 7, section 8, 1 through 41 odd. Then I'm going to have you on page 342, this is chapter 7, section 9, read it. Okay, just read it, and I put here read actively. And what I mean that's in the syllabus, what I mean by that, it's like as you read it, like write what they're doing along as you're doing it. Like all this is proofs. And in fact, there are 2 proofs that we did in class before. But they're kind of a different take on it, and it would be a good idea, or it would be a good exercise for you to see it from a different point of view. And anytime, if you're doing math ever, it's good to put pencil to paper, right? Math is not a spectator sport, right? So, like, write this stuff out as you read it, and it'll sink further into your brain. It's a good thing to do, good exercise. So, just do that. I'm not going to collect any homework on it, but, you know, who knows? You might see something from there in the future. It would be good for you to read, okay? But today, we're just going to be talking about section 8 here. And that is parallel and perpendicular lines. So parallel lines, we're going to define those as lines in the same plane that never intersect. Now, what we mean by plane is a flat two-dimensional space, right? Two-dimensional, very simple, right? It has an x direction and a y direction, right? And it's really important that it's flat because famously, Euclid's parallel postulate is a postulate and not a theorem. The difference between the two, a theorem is a statement with proof, right? Something that you say, for instance, two parallel lines never intersect. If you prove that, then that's a theorem. But if you say, well, I conjecture that parallel lines will just say that they never intersect, like that's a postulate. You're just saying that, you can't prove it. Famously, Euclid couldn't prove this, and the missing piece that he did not consider, or I mean, was it even possible to consider at the time, is that we're talking that it is true as long as your space is flat. But he didn't have the idea of a plane that could be, or a two-dimensional space that could be, say, curved. And if you are in a curved two-dimensional space, then it's possible that parallel lines might intersect. They might intersect at multiple points, or they might get infinitely far away from each other. What? Well, that's a little bit beyond what we're ready for here. So we'll go with this. Parallel lines are lines in the same plane, a flat two-dimensional space, just like the whiteboard here, and that never intersect. So here are 2 lines, and I'm certain that they do intersect, okay? Now, notice their slope is not the same. Yes, there's a 2 there, but one's a -2, one's a +2, right? Now, since I'm using 2 lines here, I'm going to call this first one y1, and I'm going to call this second one y2, just to keep ourselves, keep everything straight in our heads here. We're talking about 2 different lines. And this is not a point, right? Because we have been saying we have an x1, y1, and that is a point, and an x2, y2, and that's a point. It's not what we're talking about here. I'm just naming this entire line y1 to differentiate between y1 and y2, okay? Now you'll see that these certainly are not parallel when I graph them. So let's do that here. Okay, so here's x, and here's y. y1 goes through at +3, goes through the y-axis at +3, and he has a negative slope. So he does this right here. Now I'm going to go ahead and label him y1 equals -2x + 3. Okay, now the other one, y2, goes through at -1 and has a positive slope here. And since we're in my class, we are going to label this, well, first off, sorry, y2 equals 2x minus 1. So just so we don't get confused which line is which, I'm going to put the actual label on the line. Now, since we're in my class, I want these points, and here, this is y2, the intercept must be 1/2, figure that out. Since this one, the intercept must be 3/2, and it looks like I've drawn this right because 1/2 is less than 3/2. Now we could see that there is some intersection right here. They intersect at that point right there. What does that mean? Well, that means that there is some x value right here, some special x value. I'm going to call it x0 because he's special. I want to set him apart from all the other x's, x0. And we're going to notice something. Now, forget about the second line here. Forget about y2. And let's just pretend that all we have is y1 equals this. If I were to plug x0 into here, what would I get? Well, if I took x0 and plugged him into here, I would have that y1 is equal to -2 times x0 plus 3. Like that. And what would that be? Well, it would be some number, and clearly x0 is something between 1/2 and 3/2, so it's just some number. I plug it in, do some calculation, and it gives me some height, right? So what I've done is I've plugged this value into y1, and out pops some height y, but in particular, that height is minus 2x0 plus 3. So minus 2x0 plus 3 is the height right there, whatever it happens to be. Maybe it's 7, maybe it's 9. Well, it has to be between -1 and 3. So whatever it is, he's right there. Maybe he's 1. Who knows? Okay. Now, okay, so that's on one hand. On the other hand, this line too has that same property because that's the same point. If I took x0, whatever it happens to be, and I plugged him into here, what would we get? Well, I would take my formula 2, like that, and instead of putting in that any old x, I would take that special x0 and plug him in. And I'd take 2 times that number, and then I'd subtract off 1, and whatever number that gives me would give me the height. And it would have to be the same height as this, because it's the same point, right? I would have 2x0 minus 1 right there, like that. And they have to be the same height, because that's the point where they intersect. Like if I chose some other x value over here, let's say, let's call this x1, some other one, it's not so special. If I plug him in, well, when I plug him into y2, I get some height out here. If I plug him into y1, I get some height out here. The heights would be different. But since this is the same point, this x0, it's special because when I plug it in, I get the same value for y, for both of the lines. In other words, what I'm saying is that these two values are equal. That is 2x0 minus 1 has to be equal to minus 2x0 plus 3. That's what it means for two lines to intersect. That there is some x value where when you plug it into the lines you get the same height value right there, and that is what we're equating here. That's what we're saying. Those two things must be equal. Okay, so that's the case where we have two lines that I know are not parallel, two lines that do intersect somewhere. So we could sum up everything that we just did in general here and say this. If two lines, call one of them y equals m1 x plus b1, in this case m1 is 2, and b1 is -1, okay? And another line, y2 equals m2 x plus b2, so we have some other slope here, m2, and another b2, which is 3. If those two lines, y1 and y2, intersect, then there's a special x0, so that when you plug x0 into the first line, and you plug x0 into the second line, then those two values that you get are equal. We'll need to remember that for when we actually prove this claim. I want to do one more quick example before we actually prove this, because when we go to prove this, we're going to do a proof by contradiction. And it could seem really weird, especially when you do that in general, that you might not understand what exactly we just did. So I'm going to show you with a specific example before we do it in general for any two lines. Let's use a specific two lines, okay? So here we go, two lines with the same slope. So let's take two lines that actually have the same slope. One of them is going to be y1 equals 2x plus 1, and the other one is y2, which is going to be 2x minus 3. Okay? Now clearly they do have the same slope, and if I were to graph these guys, you could see that they're parallel. That's not really enough for what we're trying to do. Like, it's not enough to just draw this and say, oh yeah, they're parallel, like therefore they never cut. Like we want this statement, okay? But anyway, here we go. So 2x plus 1 goes through here at 1 and has a positive slope. 2x plus 3 goes through at minus 3, and he has the same slope. So intuitively, you get this. They are going up at the same rate, right? And if they're both going up at the same rate, they have the same rise over run, they can never touch, right? Now, this would be negative 1/2 right here, and this would be 3/2 right here. Okay, anyway. So that's cool, but let's suppose, for a contradiction, let's suppose that they did intersect somewhere. So we know this is the real picture here. But now we're going to assume that these two lines with the same slope actually did intersect somewhere. So now we're looking for a contradiction. I want to see how that's going to show up when we go to do this in a general proof. So we're going to use a specific case here. And we're going to assume that these two lines actually do intersect somewhere. So let's graph these lines. One goes through here, the y2 goes through at minus 3, and he has a positive slope, like that. Okay, so that's y2. Now the other one goes through at positive 1, and he has a positive slope. So here's 1, and he has a positive slope. And let's just say I'm really terrible at drawing. And I don't bother to, like I've been saying, like, don't bother to do it right. You just draw it. And you go, hey, look, these guys do have an intersection point. Now real quick, let's do this. So that was y2, this is y1, which is 2x plus 1. And so he must go through at negative 1/2. He must go through at 3/2. And it's starting to look like my picture is qualitatively accurate, because maybe they do. How do I know? Maybe they do actually intersect at some point. And so we would say, if they intersect at this point, then there's a special value, right? This is what it means. If these lines intersect, then there's a special x0, which has the property that when I plug it into y1, I get out, well, let's see, 2x0 plus 1. So I plug x0 into y1 and I get out 2x0 plus 1. 2x0 plus 1 right there. But since these lines intersect, we have the property that when I plug it into the second line, I get the same value. So I take my x0, plug them into y2, and I get 2x0 minus 3, which is the same thing. 2x0 minus 3, there's my x0. And so we say, okay, well then they're equal to each other. 2x0 minus 3 is equal to 2x0 plus 1. And let's see what happens here. If we assume, now remember, this is a contradiction. This is not actually true, but we're going to see how this shows up. What does this look like? you say, okay, if those two lines that have the same slope actually do intersect, well, they intersect at some point, and that means that their output values are the same. And now let's just solve. And I'm going to say, okay, let's subtract off the 2x0s from both sides, because whatever number that is, maybe it's 5, well then that's also 5, right? Whatever x0 happens to be, you plug it in and you get a 5, whatever it is. Well, let's just minus it off. So minus 2x0 from both sides. I'm going to do it over here, minus 2x0, because it's just a number, I could do that. And now I get, well, that guy's gone, and I get negative 3 on this side. That guy's gone. I get positive 1 on that side. So I get that negative 3 equals 1. Does negative 3 equal 1? No, wait a minute. This is a contradiction. This is a contradiction. Negative 3 is not equal to 1. And so we could kind of work our way backwards and say, well, if negative 3 is not equal to 1, then there's no, this is not true. Therefore, there's no x0 value which will make this true. And if there's no x0 value which makes this true, then those lines can't ever intersect. There's no special point that you could plug in to each of those lines and get them to work. So we could conclude that this line and this line are parallel, because if they did intersect, well, you would get junk. Like, this just simply is not true. I hope that makes sense, right? This is what we're saying, like, and now we want, and I wanted you to see this, and maybe this is just very obvious, like, okay, I can see how that works. I wanted to work through this because when we go to do this in general, we get down to this point and say, hey, negative 3 is not equal to 1, and you go, what does that have to do with these lines? Well, this is what it is. It's kind of when you start working your way backwards, you end up at a contradiction, and you have to work your way back and say, well, what did I do wrong here? Well, that's fine. Well, it must be that there is no x that makes that true. And if there's no x that makes that true, then they must never touch, right? So that's what we're going to do now in general. Two lines with the same slope are either parallel or they're the same line. Here's your proof. First off, notice that all lines have this form. All lines have a form y equals some number times x plus some other number. Okay? This, of course, whatever goes in there is the slope, right? And this is just whatever the height is, you know, on the y-axis. Okay, the y-intercept. So, okay, what do we have here? Two lines with the same slope. So let's take any two lines with the same slope. So any two lines with the same slope have this form. y1 equals m for some m. Y, it could be any number. X plus b is any number. Okay? And y2 equals the same m. Notice that has to be the same for them to have the same slope. X plus, it could be any other number. Let's call it c. Okay? So we have a y1 and a y2. Now before we continue, let's just graph these in general. And we're gonna now, for a this is what we're actually, before we do that, we're gonna, for a contradiction here, we're gonna assume, and I'm gonna say this explicitly, for a contradiction, assume they do intersect. It's really trying to cram it in there. That's what we're going to do right now. We're going to say, hey, okay, well, these two lines have the same slope. Let's just assume that they do intersect somewhere. Same thing we did just a minute ago. We have two lines, okay? It's this one and this one. They do intersect somewhere, okay? At some special value of x0, where the outputs are the same. Okay? Then by what we said right here, there is a special x0 so that these two, they have the same output values. So then, since they do intersect, which they don't, but we're assuming for a contradiction that they do. If they do intersect, then there is a special x0. We'll use colors here. A special x0. So that plug it into the first one, and it equals the exact same thing as the second one. So let's do that. Plug it into the first one, y1 equals mx0 plus b. Right? So plug in x0, you get out your y1, which is mx0 plus b. And it has to be equal to what you get when you plug it into the second one, mx0 plus c, which is y2. And that's what we're saying here, right? You have your y1 and your y2, you plug in your special value x0, and the two heights, the output values, y1 and y2, are the same. Okay. I'm going to drop the blue now, right? I'm not going to use blue anymore because it's going to get ugly. So in other words, what we're just saying is that mx0 plus b is the same thing as mx0 plus c. Well, we're going to use the same trick that we just did a minute ago. We're going to say m, which is whatever number it is, times x0, is the same thing as m, whatever number it is, times x0. So I can subtract off from both sides. And that leaves me with b equals c. Now, suppose that they're actually the same number. If b is 5 and c is 5, that is, if b and c are the same, then they're the same line, right? Doesn't matter what n is. If I said m was 27, 27x plus, and b happened to be 5, is that the same thing as, well, m is 27x plus 5? Oh yeah, it's the same line, and this is like why at the very beginning we talked about this in the first place. Oh yeah, if b and c are actually the same, then you do get the same line. With that would be our conclusion. If b equals, we end up with b equals c, and if they're actually 5 and 5, then yes, they're the same. And so that implies statement 2 right there. Okay? So that's the first case. But if b and c are not the same, if b is not equal to c, then you have a contradiction. Just like we ended up with a minute ago. Negative 3 equals 1. Does negative 3 equal 1? No. Then there must not be. So if b is actually not equal to c in the formulas that you had at the beginning, just like we did a minute ago with positive 3 and minus 1, or whatever it was, right? We could see like, oh, no, those actually aren't equal, and therefore there's no x0 that has this property. No x0 works. So we must conclude that the two lines don't intersect. So the two lines don't intersect. If the two lines don't intersect, then they're parallel. That's what it means. So this implies, therefore, it must be 1. So we had two possibilities. We did our work. We assumed there was we assumed that they actually intersected, right? We had two lines with the same slope. We started with the assumption. You have two lines with the same slope. There's two lines with the same slope. And we said, well, if they do intersect, then it has to be the case that b equals c. And if b is actually equal to c in your original formulas, then, well, then they're the same line, aren't they? But if they don't have the same value, so you have 2x plus 1 and 2x plus 3, or 2x minus 7 and 2x plus 8, you end up with 7 plus 8. Well, that's not true. So there must be no place where they do intersect, and therefore, if they don't intersect, they are parallel. And that is what we wanted to show. QED. So we conclude parallel lines have the same slope. Now, this is why it's kind of important to say, like, that it's not that this line has no slope, right? A horizontal line has the equation y equals, say, 7, or y equals, say, 1, but really it's 0x plus 1, and this one is 0x plus 7. It has a perfectly good slope. It's equal to 0. Now, there's one case we haven't really talked about, and that's vertical lines. Vertical lines don't have a slope. So that would be, yeah, we just have to think about that though. And if you have a vertical line, say x equals 1, okay, so there's your vertical line, and you have another line, say x equals 5, okay, do those ever intersect? Well, no, there's no special x0 where they actually are equal to each other. And if you want, you could go through and do another proof like we just did. But everything we just said about intersecting lines mean that they intersect somewhere on the plane. If they intersect somewhere on the plane, there's a special x value where they actually touch. Like this one and this one intersect at here. That's the special x value would, I guess, be x equals 5. And so on, right? Well, here, two vertical lines, it's the same argument. There's no x0 where they're actually the same because the x is always exactly the same for this. X is always equal to 1 no matter where you are on the plane. For this vertical line, x is always equal to 5 wherever you are on the plane. There's never a place where you have an x0 that's the same between them. So, but like I've said a bunch of times, we really don't care about vertical lines. I mean, it's rare that we talk about vertical lines at all. There's a better way of treating them. But right now, we're just going to go with this. Parallel lines have the same slope. Now, let's do an example from the book, because this is how we're going to use this fact right here. Number 10 says determine if the two lines are parallel. And here's the two lines it gives you. -4 equals y plus 2x and 6x plus 3y equals 4. You could graph them, but that's still not going to tell you anything, because what if you graph them wrong? What if you didn't get your slope just right? And what if the slopes were barely, and that's the thing, like, even if you were to plug something into Desmos and you look and you see, well, they look like they're going in the same direction, what if they're just barely off? And it's not until you get out to 100 billion before they actually touch. Well, you'd never see that, right? So the idea is we're going to use this fact. Parallel lines have the same slope. If we find the slope of this line, and we find the slope of that line, and they're the same, then the lines are parallel. So it's simply, let's just find the slope here. I'm going to bring this, I'm going to get y by itself. I see this equation, I'm like, if I just get y by itself, well, that's easy. I'll subtract 2x from both sides. I get minus 2x minus 4 over here. Over here, I get, well, now I have my 3y, I'm going to stay put, minus 6x plus 4. Now I'm going to go through and divide by 3, y equals negative, I guess that's negative 2x plus 4/3. Now, now they have the same slope. Are they the same line? No, they're not, because they have different heights, right? Or I'm sorry, they have different y-intercepts, right? One of them is down here at -4, and he's -2, -2x. That's that one. This one is -2x, but he's up here at 4/3. So be careful with that, because what if they gave you? What if it worked out that this one was also -4? Well, they wouldn't be parallel lines, they'd be the same line, right? So careful with that, but clearly, right, this should be obvious. These are parallel because they have the same slope, and they're not the same line. But I'm not gonna bother saying that every time. Maybe I should, because that's like the kind of trick that gets you. But anyway, do check that they're not exactly the same line. These lines are parallel. Okay, new definition. Perpendicular lines are lines that intersect at a 90-degree angle. Okay? Now, our goal, what we're trying to do here, is we want to see how the slopes of perpendicular lines are related to each other. Because clearly, it's the slope that determines whether two lines are perpendicular, right? If you have like a slope like this, well, if they're the same slope, clearly they're like parallel. But if they're like, it depends on the slope of the other one before they get to like a 90-degree angle between them. Now, one thing we need to notice right away is that the x and the y axes are at a 90-degree angle from each other. It's almost by definition, we choose to put the x one horizontally and the y one perfectly vertically. And so, if you think about say a circle has 360 degrees, if you go all the way around, you're at 360 degrees. If you go half that distance, you're at 180 degrees. And if you half that again so that you're up at the top, it's 90 degrees. In other words, if you chop a circle into 4 equal sectors like that, just like we do with an x and a y axis, we don't bother to draw the circle, but really you could draw any circle around the middle and you'd see like, yeah, if we're measuring this way, from the x-axis to the y-axis, by definition, that is 90 degrees. If it's not, then you didn't draw your axes the right way, right? So it's just kind of like, I mean, by definition of what degrees are. We say that 360 gets you all the way around. So halfway around from here all the way to there would be 180. And so half of that from horizontal to vertical is 90, right? And that's how we construct the x and y axes. So that's the first thing to notice. So take any line y equals mx plus b. And what we want to do is construct a line that's perpendicular to it at any point. Let's say this point right there. Now what we're going to need to do, since we want to relate slopes together, is we need to find the slope of this line. Yes, the slope is m, but we need a rise and a run for what we're about to do. So I start at my point and run any distance to the right, due right, parallel to the x-axis. That's how we've defined the run of when finding slope, we define the run as you run exactly to the right, which is parallel to the x-axis. This is the run. So we run some distance to the right. Then we run directly up, parallel to the y-axis. We'll call that the rise. Now let's give these actual names. Let's call the run A. We'll say that this distance from there to there is A. We'll call the rise, the distance from there to there, B. Okay? So we have the rise, which is B, and B is positive in this case, though that won't really matter. And the run is always positive because we decide that we're going to run from the right to the left. So, right now we have our slope. And I'm going to go ahead and write that. We know, because of this equation, y equals mx plus b, that m must be rise over run, which in this case is b over a. There you go. Now, if I wanted to construct a perpendicular line, one way we could do that is to think about if I took, let's say I took this entire line and I put a pin right through that dot right there. And if I put a pin through the dot, then I can move the line, but the pin stays put, right? A perpendicular line, by definition, the intersection is at a 90-degree angle. So if I took this right here, took this line, put a pin through it at that dot, and then I rotated it 90 degrees, we would, by definition, have a perpendicular line. But how do you know how far 90 degrees are? Well, think about this right here. The run is parallel to the x-axis. And so if I put a hole through right here at the run, and I brought him 90 degrees up, if I rotated the run 90 degrees, then by definition he would have to be parallel to the y-axis, because these guys are 90 degrees from each other, right? Start here at the origin and rotate 90 degrees and you're due vertical. You're due horizontal here, rotate up 90 degrees, you're due vertical, right? And so, same thing here. If I took this and rotated, because this is parallel to the x-axis, if I rotated him 90 degrees, then this run would then be straight up and down. Or if I thought about this as a triangle right here, there's my triangle. It has, this length is A, and this length is B. And I took him and put him right here on this dot and rotated him 90 degrees. Well then, it must be the case that the run is now due vertical. And if the run is exactly vertical now, then this guy, since he's at a right angle, he must be due horizontal, right? By the same argument. If you started here, right there, and rotated 90 degrees, then since he was vertical, he'll end up exactly horizontal. Same way as if you started with a vertical line here and you rotated it 90 degrees, it would then become a horizontal line. So that's what we're going to do here. We're going to take our rise and our run. Well, first, we're going to take our line and we're going to put a pin in him right here. And we are going to move this entire line so that it moves about this line. And as you do that, this guy who's here, he would be pushing along until he gets so that what was the run is exactly vertical now. The former run, A, is now parallel to the y-axis. So I'm going to go ahead and draw that now. So here's this guy, and we're just going to draw the new run. The old run is now straight up and down. Similarly, the old rise, B, is now flat. He is exactly horizontal, like this. And then that means then that the line that we've rotated would have stayed on this side of this guy the whole time, and he would be right here. So let's draw that line coming down through here. Oops. Okay. So here, now we have constructed a perpendicular line. He comes through like this. All right, there we go. So that's our perpendicular line. What's the slope of that perpendicular line? Well, let's stop for a second and say, this is a line, therefore it has the form y equals mx plus b. But we just used an m. Let's not use m. Okay? And let's not use b, because that's a b. Let's call this line right here y equals, how about lowercase n x plus, how about c? Okay? Now let's find the slope of n. Well, to find the slope, you start at any point and run some distance and then rise or fall some distance. Oh, hey, look at that. That's real easy to deal with. Let's look at this. So this length we called A, and when we brought him up, that's the same length right there. That's still A. This length was B, and now when we bring him up, it's still B right there. So we have a run in this case. We know that n is rise over run. And for this line, from this point to this point, the run is b. Now the rise for this guy, since he's coming down by the way that we drew this, then the A must actually, it's not a rise, it's a fall. So it must be a negative number, minus A, right there. Now, on the other hand, if we had started with a negative 1, well, we'll do that in just a second. But let's just look at this right here. What do we have? So, how could we relate these two things together? One way to think about this is that, well, perpendicular lines have the property that whatever the rise is for one of them becomes the run for the other. And whatever the run is becomes the rise, and then it has this interesting negative relationship. And let's just see, because maybe this is just an artifact of the fact that I started with a positive line, and now when I rotate it, now the other one's negative. What happens if I start with a slope that's negative? So we just showed that you have any line and its slope, if its slope is b over a, then a line that's perpendicular to it has a slope negative a over b. Does that depend on the fact that the m was positive? Well, let's do the same thing here. Let's say that y equals mx plus b, but now the slope is actually negative, okay? So in this case, the rise is a negative b, the run is a positive a, and we get that m is negative b over a, okay? And now we rotate this guy 90 degrees to get our parallel line. And so I'm going to do that right here. And, oops. There he is right there. And goes on forever the other direction, like that, okay? Now, it's terrible. So now the rise is A, and the run is B in absolute value here, right? We're going to say this line has the equation y equals nx plus c, and n is the rise over the run. In this case, the rise is A, the run is B, so it's n equals A over B. You see, it has this same relationship. If one is positive, the other's negative. If one's negative, the other's positive. Now, maybe you didn't like this because, well, it's like, well, you said that m should be positive b over positive a. Well, hold up, does this matter? Right? Who said that this one had to be that one? Why not call this one m? So that's m. And call this one n. So that that's n. And this is n. And then you say, well, that's still not the same. N is supposed to be negative a over b. Well, then just rename these things, okay? We'll rename this minus a, and we'll rename this b. And, and we could go through and do all this, right? And in which case, this would be a negative a over b. And then we'll just rename this, since that's a b. And that's an A. He's now positive because he's coming up, and so we have rise is B over A. But I think a better way of thinking about this is, look at this. Slope is rise over run. If B is a negative number, right, let's say that B were like negative 3 and A is whatever it is, then flipping it, right, this is what it says to make the perpendicular slope is you flip the A and the B, right? So the A comes up top, the B goes downstairs, and then it says make the A negative. But a negative negative is a positive, right? So if that one's negative, then this one's positive. In other words, it must be the case that if one is negative, the other one's positive. If one's positive, the other one's negative. And the way that you do that is you just make the second one negative. If the original if this one had started off as a negative number, and indeed it was a fall and not a rise, then when you make the second one negative, you make a negative negative to make it positive. That was a 3. Excuse me. So I hope that makes sense. We have achieved our goal. We have seen how the slopes of two perpendicular lines are related. We could say that if this line and that line are perpendicular, the first one has slope m, the second one has slope n, then they have this relationship here. M is rise over run, and then n is negative run over rise. Another way we could say this, there's a few equivalent ways of saying this, is that m times n equals, well, let's find out. M is b over a, n is negative a over b, so that's b times negative a over a times b. Well, the b's cancel, you get negative a over a, which is negative 1. So that is another way of saying this. Was the first way of saying it. The second way of saying it is that if two lines, mx plus b and nx plus c, are perpendicular, then their slopes, m times n, is equal to negative 1. And if that's true, let's just look at this. I could take this equation, mn equals negative 1, and divide both sides by n. And this is probably the most useful way of this, is that the slopes are negative reciprocals of each other. That is, if mx plus b and nx plus c are perpendicular, then one of them is negative 1 over the other. And similarly, I could have taken this, mn equals negative 1, and divided both sides by m. M's are gone. N equals negative 1 over m. And so n is equal to negative 1 over the other. Again, it's negative 1 over the other is how they're related. And so, for instance, like there's a few ways. So these are all equivalent ways of saying the same thing. These two lines are perpendicular, then the rise and the run flip, and you make the other negative. That's nice because if you have a slope that's like negative 2/3 and you want to find the perpendicular slope, which from now on I'm going to write like this, m perp, and that's how it's said in math when you write that little symbol, perp, for perpendicular, and that's pretty obvious why this is perpendicular. You know, makes sense. M perp is perpendicular, is the perpendicular slope to m. So if you have an m, then the perpendicular slope to it is you flip this is how you use this first one. You flip the roles of rise and run, 3, 2, and then you make it negative. So if it was negative, it becomes positive, right? So that's how you use this one. Given some m, and let's do another one. How about 3 halves? The perpendicular slope to that one is, well, flip the rise and the run and make it negative. If it was negative to start off with, it becomes positive, right? They have to have that relationship. If one's negative, the other's positive. Another way to do it, using this fact right here, is like if you have your m is equal to 2, you're like, well, there is no rise and run. Well, it actually is. It's 2 over 1, so flip it, right? Like, this is actually 2 over 1. So then, using the first way, you say, well, flip it, it's 1 over 2, and then you make it negative. Or, you could say, well, hold up, I could just do this, that the perpendicular one is negative 1 over whatever that one was. And so that's 2, that's negative 1/2. This also works this way, too, that if m is 3 halves, then the perpendicular slope to it is negative 1 over whatever m is. 3/2, which is -1 times multiplied by the reciprocal, 2/3, -2/3, which is what you get by just flipping rise and run and so on and so forth. But it's all consistent. This is how you use this. This is the relationship we were looking for, and that's how you use it to find a slope that's perpendicular to a given slope. So we have two problems. It says, what's the slope of a line perpendicular to y equals 2x plus 3? And the next one is, what's the slope of a line perpendicular to y equals -3/5 x plus 7? Pause the video and see if you could figure these out on your own. Okay, welcome back. So, the slope perpendicular to. So, all of this comes down to, if you know the slope of one line and you want the slope of a line perpendicular to it, it comes down to that. So, the given slope of this line is 2. Now, you could use either of these ways of doing it. In fact, I'm going to use both ways of doing it. One way you could think, and this is how I think, well, hold up, rise over run. I don't see a run, but I know that that's actually 2/1. And so to get a perpendicular slope, I'm just going to flip rise and run and then make the entire thing negative. There you go, right? And that's this formula right here. It says imperp is if you have a b, if you have a b over a, and so in this case I'm thinking of m as 2/1, this thing says flip it, make it 1/2, make it negative. So that's that way of doing it. Another way of doing it would be to say, okay, I know that the perpendicular slope is -1 over the original slope that I had. And so my original slope was 2. Oh, there it is. M equals, again, -1/2. No matter how you want to do it, right? So that, sorry. So the slope of a line perpendicular to this one must be -1/2. And we could do the other one exactly the same way here. Our given slope, the slope of the line that we're given, is m equals -3/5. And the way I like to do it is I just take the number, flip rise and run, right? So the 5 comes upstairs, the 3 goes downstairs, and then I make the entire thing negative, which has the effect of making the entire thing positive, right? You can think about this as a -3 there, and then if you make that negative, you have a negative and a negative, which is a positive. Or you could just flip the sign, right? Like the way I originally wrote it is how I probably would do it. I would just say, okay, rise becomes run, and run becomes rise, and if it's negative, it becomes positive. And you're done. If it's positive, it becomes negative. Now, the other way is to say, okay, the perpendicular slope is -1 over the original slope. And the original slope was -3/5. Now we have to do some calculation. You're dividing by a fraction, so we're going to multiply the numerator by the reciprocal. So the numerator is -1. And we multiply by the reciprocal of this, which would be -5/3. Negative times a negative is a positive, so that's, positive 5/3, there you go. However you want to do it, you end up with the slope perpendicular, the slope of a line that is perpendicular to this line will be positive 5/3. Problem 18 says, determine if the two lines are perpendicular, and they give you two lines. Well, whether or not something's perpendicular comes all down to the slope. So if we could find the slope of these lines, we could compare them and see if they have that relationship that we're looking for, right? So I'm going to take the one on the left and get it into the form y equals mx plus b. That means get the y all by itself. So we have 6y over here, -2x right there, and then -3. Divide through by 6, divide everybody through by 6, and now I get y equals -1/3 x minus, is that 1/2? Yeah. Okay, so that's the first line. Second line, The y is already on its one side by itself, so that's nice. Let's go ahead and divide everybody by 12. 12. Y equals 4 and 12. I guess that's 3 left over, so 1/3 x plus whatever this is. It actually doesn't matter. What's that? 10/6, so 5/3? 5/3? Actually, it does kind of matter, because if they're the same line... Well, no, we were talking parallel and perpendicular. Okay. Now, here's the thing. You might say, like, you look at this, you go, oh, one's positive, one's negative. Yeah, but that's not... They are not perpendicular. Right? Now, another one... The way that I would do this is I would get, once I got to this point, I would say, let me find the slope that's perpendicular to this. That is, if this is m minus 1/3, then m perp, the perpendicular slope, is going to be, I flip the role of rise and run, I get 3/1. If it's negative, I make it positive. If it's positive, I make it negative, so it has the opposite sign. There you go. Now, we could just, this is the way I prefer to do it. You just say, well, that's what any line that's perpendicular to this line must have this slope right there. Is that slope? No, it's not. It is not that slope. And conversely, if you had started with this one, you said, okay, well, if m is 1/3, then the slope that's perpendicular to it would be, I swap the roles of rise and run, and then I make it negative. If it's positive, if it's negative. And so that's -3. And then I just ask myself, is -3 that number right there? No. So then they are not perpendicular to each other. Now, another way you could do this is, remember, one thing I haven't written up here with all these relationships between slope and everything, the way I wrote it before was m times n, where m and n were slopes of perpendicular lines. Well, here we could write this as m times m perp is -1. And this is probably the way your book is looking for you to do it, but I think it's a terrible way of doing it. You just take the two slopes, multiply them together, and see, does it equal -1? And so I could take this slope here, and here, I'll go ahead and get rid of this stuff. You could do it this way. I'm going to tell you why I'm going to ask that you don't. Here. So doing it this way, you say, okay, here's your slope, m1, and it's -1/3. Here's your slope over here, it's a different slope, so I'm going to call it m2, and it's +1/3. Now, if I multiply them together, and I get a -1, then they're perpendicular by definition. And so -1/3 times 1/3 is -1, oh, almost, but over 9. Oh, yikes. So that's not perpendicular because by definition this is a blah, blah, blah. The problem with this is you lose sight of what it is to be perpendicular. Like if you have it in your head like, the product of perpendicular slopes is -1. Like, what does that mean geometrically? Like, what does that mean in terms of rise and run? Like, let's not think about it that way. It's and just going through the motions of calculating a perpendicular slope is so good for you. Because now you're actually doing this. You're saying, hold up. If the rise and the run are 1 and 3, and it's negative, so it's a fall, then the perpendicular slope to that would have the roles of rise and run reversed, and it would be going in the opposite direction. If one is negative, the other one must be positive for them to be perpendicular. Over here, you have this, and you're thinking, okay, the roles of rise and run are flipped, and since this one's positive, the perpendicular slope must be negative, and that's kind of what's going through your head here, and you could stop anywhere along the way and compare, right? But it's good to go through this because it reminds you of what it is to be perpendicular. Rise and run are interchanged, and the slope has the opposite sign. This, you're just plugging junk into an equation and going, does that equal -1? What does that mean if it equals -1, right? So I would suggest that you do it this way. So we conclude, no, these lines are not perpendicular. So numbers 27 and 29 are related to 31 and 33. That is, 31 refers back to 27, and 33 refers back to 29. The same way 28 and 32 are related. We're going to do 32 in a second, and you'll see that it relates back to this question here. So let's do it. Write the equation of the line containing the given point, that one, and perpendicular to the given line. So can you guess what I want you to start with? That's right. Write the equation of the line. Well, let's identify what we want. It says write the equation of the line, so I'm going to write this down. What we want, our goal, is to come up with some y equals mx plus b. Now, what's the information that they gave us here? Write the equation of the line containing the given point and perpendicular to this line. Let's just go ahead and sketch out this line to kind of see what's going on here. Okay, so we have an x, we have a y. It goes through at -3 and has a positive slope, so it looks something like this. Goes through at -3. Goes through here at 3, comes over, 2 goes down, positive 3 happens. There we go. Now it contains this point, -2, 4. Okay, -2, and I'll put a 4 up here. Now, one thing to notice is I'm not drawing this stuff to scale, and so I'm going to use what I end up getting here for my perpendicular line, my y equals mx plus b. I know, like in my head, that it needs to come in at a right angle to this. That's what I'm looking for. And the thing is, the way I've drawn this slope might be way off. And like if I drew it way down like this, like then a perpendicular slope might not look right with that. But I can still use this to kind of inform, to just double check myself there at the end. So it's a good idea to just have this stuff out there. Because if it's radically different, then that'll be bad. Okay, so here's the thing. And this is what they're saying. You have a given line, that's the given line. The line that we want, our y equals mx plus b, needs to go through that point and be perpendicular. It needs to intersect here at a right angle. So now let's think about what information do we have. We're looking for an m, we're looking for a b. We don't know what b should be, but if this line, the one that I want, has to be perpendicular to that line, I can find the slope. I should say that this slope, this m, is perpendicular to this slope, 2. And so, again, I'm going to think about that as 2 over 1. And so perpendicular would mean that m, the one I'm looking for, must be -1/2, right? You could also plug it into here, -1 over that guy. That's the guy you want. Now don't get too, you're like, wait, it's a perpendicular slope. Why didn't you write a little perp here? Well, because that is the slope I want. Really, like if you really wanted to, you could call this y equals mx minus 3. And then you say that the thing that you want is a y equals m perp x plus b. And then you say, okay, if m is 2, then m perp is -1 over 2, and so on and so forth. But that's really not how I think about this. It's just like I know that I have a slope. It's m. We're going to call it m. So m equals something. What property does it have? Well, it's perpendicular to this. So flip it, you get 1 over 2. Make it negative. Since it was positive, the new slope is negative. So we're halfway there, right? I'm going to take this guy, plug him into here, and get y equals -1/2 x plus b. All that remains is to find b. But we're given a point that's on that line. This point is on the line. When I plug in a -2 for x, I get out a 4 for y. So let's do that. Because it goes through, what I'm saying here is that this goes through the ordered pair with a point minus 2, 4. Which means that if x is a negative 2, as if I plug in a negative 2 for x, I get out a 4 for y. So now, negative negative makes positive, 2 and a 2 cancel, and I get 1 plus b on the right-hand side. On the left-hand side I have 4, subtract off, and I get a b. Now I'm done, right? My y equals mx plus b is actually y equals negative 1/2 x plus 3. Now we could use our picture to assess whether or not this makes sense. It has and again, like, does this look right? Yeah, it would probably go through somewhere up here. So that would mean that my perpendicular line, the one that I'm looking for, has a negative slope. Yep, he should have a negative slope, and he has a positive y-intercept. That looks pretty good. And what I'm saying, though, is like if at the end you got y equals, say, 1/2 x minus 2, and you looked over here, you could look easily and see that that's not the case. It has to go through this point. And if it has a positive slope, then he has to come up like that. And that does not look perpendicular to that at all, right? Looking at this, you know he's got to come down to be perpendicular. Another thing, minus 2, does that make sense? Well, no, I guess if you were coming way down like this, but then you could see like that probably wouldn't be, maybe I drew it funny, but that's probably not the case. And so by having this thing drawn out, you could use that to infer, like, this does seem like a reasonable answer right there. And indeed, that is the answer. We should finally check two things, like, is this indeed perpendicular to that? And we look at the slopes to confirm that. Like, is negative 1 over that equal to that? Yeah. And vice versa, right? Swap the roles of rise and run, make it negative, and yep, you'll get that. And also, like, does it actually go through this point? If I plug in a negative 2, do I get a 4? Well, yeah, like, obviously, because you just did this. Like, you're gonna, in fact, if you plug in a negative 2, you're gonna do these same calculations, basically. But it's nice to just check that if I plug in a negative 2 into here, minus 1/2, and I plug in a negative 2 plus 3, right? I'm just checking that this point is there. When x is negative 2, does y equal 4? Well, the negative and the 2 and the 2 cancel, negative and negative make positive. 1 plus 3. 1 plus 3 is 4. So yes, when I plug in a negative 2, I get out a positive 4, so it does work. Okay, in your book, it says 31 through 34. Write an equation for the line containing the given point and parallel to the given line in each of exercises 27 through 30. So this is what I mean here. When you go to do problem 31, it's referring back to the setup from 27. When you go to do problem 33, it's referring back to the setup from 29, and therefore 32 is referring back to the setup from 28, where the given point was negative 2 comma 4, and the given line was y equals 2x minus 3. So that could be a little confusing. That's why I wanted to do this, so you could see what they're talking about. So now, okay, let's do it. Write the equation of the line containing da-da-da-da and doing da-da-da-da. Well, what do we want? We want a y equals an x plus b. Containing that point, yep, and parallel to that line. Well, we just did this, so we could do this easily again. There's x, there's y, goes through at negative 3 and has a positive slope, so it looks like that. There's negative 3, and there's 3 comes over 3/2. Did I do 2/3 last time? Did I write 2/3? I'm not sure. I'd have to go back and see. It should be 3/2. Positive 3/2. Okay, anyway, and now we have the point -2, 4. 4 is up here, and so it needs to go through there and be parallel. So what I'm looking for is something, it should go up, right? Its y-intercept should be bigger than 4, because otherwise it wouldn't be parallel, right? And so here we go. We want a y equals mx plus b, which means we need to find a m and we need to find a b. I don't know what b is. I can tell it's bigger than 4, but other than that, do I know what the slope is? Yes. If two lines are parallel, then their slopes must be the same. Again, this is the kind of thing I've been talking about, like, have what you want and then see what information you could use to fill in these gaps. And that's what we're doing here, right? Saying, okay, this is what I want, this is what I'm given. What do I know about m? Is there a way I could find m? Oh yeah, it says that the lines are parallel. That means the slopes are the same. So, since they're parallel, that means that our slope that we're looking for is the same as the slope, it's 2. So I'm going to plug that in and get y equals 2x plus some unknown b. How do we find b? Well, we've been playing this game for a while now. If we have a point, we could find one unknown. We could say that when x is equal to -2, then y must be equal to 4. When x is equal to -2, that means that y must be equal to 4 for it to go through that point. So let's plug in the x equals -2 into here. We get 2 times -2 plus b. That has to be 4. That has to give me a 4 right there. So 4 equals -2 times 2 is -4. Be careful with that. If you thought that b was equal to 0, you'd be wrong. Add 4 to that side and you get 8 equals b. And now we have everything that we need to know. Y should be m, x plus b. Y equals m is 2, x plus b plus 8. Now let's assess and see if this makes sense. He goes through this point. Does he go through that point? Plug in a negative. That's what we just did, but let's just check. Plug in a -2. And we have 2 times -2 plus 8. 2 times -2 is -4, plus 8 is a positive 4. So yes, he goes through there. He has a positive slope, so he does this right there. It's parallel. It's the same slope as that, so that looks good. His y-intercept, 8, is indeed bigger than 4. It's above 4, so that looks really good. You don't need to draw this out, but this will help you assess and see, am I on the right track here? So that's all I got for today. Oh, there's one more thing. I'm sorry, number 41. On number 41, it gives you like a drawing, and you need to find equations of lines. Don't sit there and count like how many squares there are to try to find the slope. They give you points. Use the points to actually determine for real what the slope is and all of that stuff. Please don't try to count squares and get your slope that way. Just do what we've been doing when you've been given 2 points and finding a slope. So that's all I got. I will see you guys hopefully Tuesday.